por isso que eu tô dizendo que era bem curtinho, entendeu? Só ia mostrar.
Pronto, eu acho. Não, está sendo transmitido em YouTube, Vitor. Não precisa. Tá? Só um momento. Por favor, confirma se estão conseguindo ver a tela.
Não, ainda não.
Não?
Mas tá ali.
Pode ser que não.
Esse ficou no StreamYard também?
Já, acho que no StreamYard. Please, anyone confirm in YouTube if you are able to see the screen?
Alguém entra aí? Deixa eu ver. Já sei que vai vir?
I think so. Are you able now to see the screen? Yeah, okay. Good afternoon, guys. Today we will talk about, the teacher will talk about probing dark matter particles, different dark matter particles by using electron field target experiments. So, it's yours.
Okay. So, hello everyone. Good afternoon. As Lucia said, I'm going to talk a little bit about this article, which is probing scalar direct Majorana and fermion dark matter through spin zero electron-specific mediator at the electron physics targets experiments. This paper talks about, as it says in the title, in the context of electron fixed target experiments, but since our group is more interested right now in Na64, I didn't enter so much in details about LDMX. That is another fixed target experiment that will be constructed and that is located in Fermilab, if I recall well. So, in this paper, they propose some different kind of dark matter. All of them are light dark matter, and it's in the range of 1 MeV and 1 GeV. And they propose Majorana fermion, direct fermion, scalar, and a vector dark matter. And in the context of light dark matter particles, and knowing that these particles the abundance of these particles was produced via freeze-out mechanism, just like WIMPs. So we need to propose a mediator for this that will connect the standard model with the dark matter particles itself, which is in this case a scalar mediator with spin zero. We can propose some different kind of different kind of mediators that can be spin zero, spin one, spin two, which are spin one, the dark photon that was it's highly studied in the group as well, and the dark graviton, which is spin two. In this case, it will be the spin zero, which is kind of a hidden Higgs boson, a dark boson, and they mention that would be an extension of the Higgs singlet, if I recall well. So, okay. So they present the effective Lagrangians for these cases. In the cases of, they don't open this here in the paper, but if I understood well, in the cases of the scalar Lagrangian and the vector one, these couplings are they have unity of energy, just so the unit of the Lagrangian will be conserved in energy to the 4. So they consider these couplings, which would be the coupling of the scalar mediator, which is this phi, and the proposed dark matter, like dark matter particles. And there is this coupling as well, which is the coupling between the mediator and the electron. It is important to say that this is a electron-specific mediator, so it only couples to electrons, and the only coupling you see in this paper is with electrons. It's the only process that will be considered. Talking about processes, they considered a Bremsstrahlung process, a annihilation resonant process, and yeah, this was the two processes that were more relevant in this paper. For the thermal target curves that are presented here in these graphs, they consider that the relic. Yes, I will do a zoom because it's really small. They consider that the relic density was obtained through the resonant process. There is electrons that annihilate into this scalar mediator, and then the scalar mediator decay into dark matter particles. I skipped the part above, but I will return to it in a bit. This part is just the calculations of the relic abundance, so considering the Boltzmann equations and etc. Talk about a little bit about the details of the calculations, and I think the only part relevant to say here is the part that enters in these graphs, because they compare two types of calculation for the cross section, the average cross section, which is through the integral, that is the numerical calculation in here, this equation 14. So they do the numerical calculation, and for the semi-analytical calculation, which is this 16, considering the low velocity approach, so you can expand the velocity for the thermal average cross section. So here they show, I will just show this first one, but the three of them are really similar. They show a graph where they compare the coupling constant. This alpha, in fact, is more like a fine structure constant for the dark matter, but it is in function of the coupling with the dark matter and this mediator. So it is proportional to the coupling. So it's basically considering the coupling of the dark matter with the scalar mediator, and this ratio. Thank you. And this ratio between the mass of the dark matter and the mass of this scalar. So it is also important to say that we are considering that this scalar couples mostly with the dark matter. So the branching ratio of the scalar to decaying in the dark matter is almost 1. So it almost never decays into 2 electrons. That implies that the scalar has to be at least 2 times, the mass of the scalar has to be at least 2 times the mass of the dark matter particle. So we can consider a lot of cases. We can consider like this 6 times, where the mass of the scalar is 6 times the mass of the dark matter, or in these other cases, where it's 3 times. That is the case that appears the most in the literature. But above 2 times, it's okay for us to consider. So the difference between these 3 graphs is just considering another values for this ratio and for the coupling between the dark matter and the scalar. The 3 of them are very similar. We have just some differences in the scaling of the y-axis. For the case where we consider this ratio, third, we can see that the semi-analytical calculations, which is this solid line, it deviates a little bit, quite a bit, from the numerical calculations. This, from what I understood, this was only for comparison. For the other graphs, for the only other graph in this paper, they consider the numerical calculations. So it's just a comparison. And the scalar case, you can see that it almost doesn't deviate. So these are what we obtain for the curve of the thermal target, the curve of the relic abundance of the dark matter. And further, we know the paper discuss about how the experiments can what the limits the experiments present for us in this case. So here, okay. So they start to discuss the missing energy signal. From what I understood, they consider this n, that is the number of mediators produced, the Bremsstrahlung, which would be the electron of the primary beam interacting with through a Bremsstrahlung with the nucleus of the active target, producing an electron and the scalar mediator as well. So this, in this equation, this is the electrons on target, the number of electrons on target that they have. It's related to the sensitivity of the experiment, as what I understood. And they consider the Bremsstrahlung process, and here the annihilation process. This annihilation process is related to secondary positrons. So you have the primary beam that can be an electron beam or a positron beam, but through this first beam, they interact via Bremsstrahlung, and the second positrons that are created in this electromagnetic shower, they annihilate with the electrons of the active target, and this annihilation, they produce the dark matter particles via annihilation and via a resonant process. So they consider here in this equation the energy of the secondary positrons, that it is this E plus. And yeah. So here they discuss a bit about the experiment itself. It's a good thing to show their experiment, because they talk about it and they refer to another paper that I have here that has the schematic. This to show here. Okay. This paper was a paper that I presented, the last presentation that I made in the group, that is very similar to this other paper, but instead of the dark Higgs, they consider a dark photon. which is a spin-1 mediator, but it is the dark photon as the mediator, not as the dark matter. And it's basically the same assumptions. We assume that they interact much more with the dark matter than the standard model, and they are produced via this portal. The dark matter is produced via this portal mediator. So this is the schematic of the Na64. As I said in the other paper, we consider Na64 and LDMX, but I'm going to put LDMX aside for a bit. So you have the beam that can be an electron or a positron beam. This is the target. So you have the vacuum pipe, the magnets here to accelerate, and here we have some calorimeters for electromagnetic and hadron calorimeters. And this is the beam line. So in this case, we were looking for a dark photon. So this is the representation of the missing energy signal of a dark photon. That is, it wouldn't have a signal that would be captured. And the same thing will happen in the case of the dark Higgs. So it was just to show the schematic of the Na64, which is a fixed target experiment that is located in CERN. They talk a little bit about in here, North area, with a beam from the SPMS, the super proton synchrotron. And they have energy, the beam with an energy of 100 GeV, so ultra relativistic electrons. And here they, as in the beginning of the paper, they show some equations and to calculate the relic target and etc. So here they put the parameters, the benchmark parameters that will be considered in the case of the Na64. And they say here too about the efficiencies that will enter in the calculation for the number here, the number of mediators produced. Here we have the efficiency of production of mediators through Branch-Shalom and through annihilation. Here they talk a little bit about the LDMX, but I will jump this part. And I will talk about this graph in a moment. So in the final part, they compare the limits of the Here they calculate the cross section with FAMCalc. I mean, as I said, they only calculate numerically. They just compare the semi-analytical part, but they calculate numerically using FAMCalc package in Mathematica. The cross sections and the decay widths for all the dark matter particle cases, so scalar, Majorana, Dirac, and vector dark matter. As I said earlier, they consider that the decay width, total decay width, is approximately the decay width from the mediator to the dark matter. So it implies that the mediator decays very little in the electron-positron pair. So here they present the cross sections, and further they present this is only for comparison that they show. They present, here are the cross sections from the inverse. So dark matter producing, annihilating into this scalar, which decays into the pair. These cross-sections are used to calculate the first graph that I showed, which would be the relic density. So when it occurs the freeze out, this cross-section stops occurring so much. So that's why they show these values
So
here.
essentially, the difference
Also.
is just the power in the beta.
Yeah, this beta is the velocities.
It's associated to the velocity.
Yeah, basically it is this difference when they consider as well the velocity, this smaller velocity. You can see a bit more difference because especially in the scalar case, because it is the only S wave case. The other ones are P wave. They have a dependency on the V squared. So, and then they show the results, which are basically in that graph above that I showed. They considered for both cases, for the LDMX and for the NA64, that the number of mediators, the sign that we are produced, is the sum of the Bremsstrahlung and the annihilation signals. So we can see here above the final graph. I will show the scalar one because it's the most different. Here. So it is a graph similar to the okay. It is similar to the first one. This line here would be the line we saw, similar to the line we saw in the first one. It's not equal because in the first graph we considered in the X that we had a dependency on the mass of the dark matter particle. Here we have dependency on the mass of the scalar mediator. But essentially it is similar curve to what I showed earlier. And the y-axis is, it's the same one from earlier, dependent on the coupling between the dark matter and the mediator, and this ratio between the dark matter and the mediator. So here they show the limits. Basically, what they exclude, they compare to in other cases. Here, the E137, they don't talk about it too much. They just talk about this Babard. This Babard is the monophoton limit. The green shade region is another electron beam dump experiment, the E137, and here we have the Na64 limit. This case, this is blue. Oh, sorry, someone said something. No, okay.
Actually, I wanted to ask, do they talk about Bell?
Sorry.
Do they talk about Bell experiment?
No,
No. Okay.
They don't mention it.
Yeah, good, thank you.
Yeah, and I didn't know much about this experiment as well. I will search for it later. Thank you for pointing it out.
Bell is E plus E minus. It's running now. Bell 2 is running.
Oh, I didn't know this experiment. Thank you for saying.
Yeah, I think it's in Japan.
Oh, okay. Later, I will want a reference from you for this experiment, if you can send me. Okay, so here they show the Na64 limits. This blue line, it's reference to a primary beam of electrons, and this red line is referring to a primary beams of positrons. In the other aspects, they say that it doesn't have much difference if you consider a beam of electrons or positrons, but in this area, which is the resonance, yeah, they are considering the annihilation process, which this is the area of resonance. There is a difference, and I believe because they don't talk too much about what causes this difference, but I believe it's related to the fact that if you have a primary beams of positrons, in the case of beam of electrons, you will have the positrons of just the positrons of the secondary beam, which are produced after the brainstorm, and these positrons will annihilate and cause this resonance process. In the case of a beam of only positrons, you have the primary positrons and the secondary positrons to contribute to this part. This is what I assume, because they doesn't enter too much about the reason. So this purple dashed line is a prospect, a future increasing of the sensitivity of the Na64. This 9 times 1011 EOT, electrons on target, is what they already have. This is a future value, and this is the future value as well for the LDMX, which is 10 to the 15, which is a very good value for this electrons on target. But as I said, we in the group, we doesn't have much contact with LDMX. Sorry, let me. Onde eu vejo? Okay. Yeah, we don't study much about the LDMX that is in the Fermilab. So this line here, the scalar, the N, as I said, was related to the thermal relic, and you can see here that it is almost all the line is excluded. In the case of the scalar, only a little part, a little region is excluded. If we consider the increasing in the sensitivity, you have a lot more parts that are excluded. In the other cases, you can see that the Na64 already excludes a big part of the Majorana, almost all of the Dirac dark matter, and all of the vector dark matter. But it is important to say that this is considering a specific ratio and specific values that are a little bit arbitrary. So we can change this ratio. We can put 1/1/6. We can put, any value that we want, considering that it is bigger than half. And we can change this coupling as well, as they changed earlier. We can put it, we can consider that is 0.1. We can put it smaller coupling or whatever. So this region can be considering different parameters. The scalar dark matter or the other cases can be more excluded or less excluded. So it's just important to know that this exclusion, it is for this specific case. So maybe the vector dark matter is not excluded if you consider another ratio. In the case of the vector, they don't tell why, but they consider 2/5, and I didn't see that.
And just ask, in this case, these four models of dark matter, right?
Mm-hmm.
So this scalar is a complex scalar, or is a real scalar?
I believe it is a real scalar. No, it's not a pseudo scalar. It's a real scalar.
Okay, so another question is, there is just one mediator?
Yeah, only one mediator that only the scalar mediator is like a dark Higgs, and it only interacts in this case with the electron. It's electron specific mediator.
Okay, so it's a very simple extension.
Yeah, it's a very simple extension and specific. So yeah, in the case of the vector, they don't talk anything about why they consider 2/5 different from the other cases, but they consider it. Yeah, and it's a bit arbitrary. So it is basically this. They get to the conclusion that with this sensitivity, the current sensitivity, the Na64 excludes a large region of many cases of dark matter particles, and the scalar is the most free one, the most interesting one to study, because it is the less constrained type. But this constraint can improve if we consider further enhancements of this electron target value. So it's basically this. And yeah, this is the calculation of the thermal target and the conclusion.
Can you again please just send these two papers of the dark photon one? Right? There is one which is a dark photon.
The
last one.
Yes.
And this one in the group, please.
Oh, I can. I will send you. This paper is related to another paper. We are studying this paper because our group is working in another paper, considering another types of light dark matter, not only this scalar mediator, electron specific scalar mediator, but another types of mediator. As the paper was not published yet, I will not talk much about this paper, but it is very interesting for our group now. This area, and in this paper we will produce another relic abundance lines for another types of dark matter, and another kinds of ratio from dark matter to the mediator that we consider, that can be dark photon and etc. And we will compare it to the sensitivity of Na64 specifically. So yeah, that's basically it. So any questions? Any appointments? Let me see if there is. Oh, Ricardo, you raise your hand?
No, I pressed the wrong button. I was applauding.
I only realized that all this time my head was in the end of this.
Yeah, half.
Yeah, because it was pointed to Lucia, so she's taller than me. Nice to know that it's recorded. Thank you. Yes. No, Ricardo will not.
I was trying to applaud.
Okay. Is a no. Thank you, Gabi. Gabi sending me the bell experiment. Okay. Gabi,
Yeah, so I did a quick Google search, and apparently Bell 2 should have a sensitivity. Can I share?
Oh, you can share. Let me stop sharing my screen.
Okay. I cannot see your screen. Can you see that? So I just did a quick Google search. I'm not sure if this is the correct channel or anything, but I would expect something like this. Some limit for Bell 2 that is a little greater than Babar, and then A64 because they have a very large luminosity. Okay.
Okay.
So I think if you are interested at E plus E minus colliders, you should check Bell 2 that is running right now. So maybe they didn't do this specific channel analysis yet, but that should be something interesting as well. Okay.
Oh, I will look for it. Thank you.
Yeah. You can send you this plot.
Oh yeah, send in the group, please. This paper.
Okay. So do we stop sharing?
Okay, so if there are no more questions, the meeting will end earlier because it was only my presentation today. So yeah, more time to do anything in Friday. Yeah, so thank you, everyone. I will end the meeting now. Bye-bye.
Bye-bye.
Okay.